going. Okay.
So yes, let's start now and they'll join.
Okay. Sounds good. Let me share my screen and let me know when you can see my screen. Okay. I hope all of you can see my screen. Yeah. Yeah. All of you can see my screen. Yeah. I'm just putting the chat window open. Is my screen visible?
Yeah, it is.
Okay, great. Okay. So hello everyone. I'm Vijender and today we'll talk about RAG that actually ships. Okay. So we'll talk about retrieval augmented generation and this is an important topic from the perspective of Gen AI. Okay. So let's get going. So what is RAG? Okay. So RAG stands for Retrieval Augmented Generation. Okay. And there are various components in this. Okay. As shown in this diagram. Okay. So I'll talk in detail and of each component I'll talk in detail. But right now, I just want you to get a very high level visual understanding that there are so many components involved in building a RAG application, correct? So you have documents which you encode using an embedding model, and then you place the embeddings in a vector database, right? And then the user queries, it gets encoded using the same embedding model. And then a similarity search is done using cosine similarity. And then the similar documents are fetched from the vector database. And along with that, a prompt is sent to an LLM and then a response is sent back. Okay. So this is at a high level what RAG is. Okay. Retrieval augmented generation. What we'll do is we'll dive deep into each component separately to understand how it works and all that. Okay. So again, RAG is a technique that combines information retrieval with generative AI to produce more accurate, contextual, and grounded responses. Okay. So what is the core problem, right? Why do we need RAG? Okay. So typically we know that when you ask ChatGPT a question, ChatGPT is able to answer the question, correct? So let's say you're asking questions like what is the capital of India, it will be able to answer, or whatever is there in public domain, it can answer, correct? And even if it is, even if the model doesn't know, like ChatGPT doesn't know, if you still ask a question, you can see that it will say searching the web. Okay. So if I just see over here, I say, suppose I say ChatGPT, right over here. Okay. So what is the capital of India? It is able to answer, right? So if you see, if I ask what's the capital of India, it will be immediately able to answer it, right? I think there's some problem with ChatGPT today. Okay, 1 second. What's the capital of India? So it will be able to answer it. I think there's some problem going on today. There's some Cloudflare challenges coming today. Yeah.
I think our network is flat.
Okay. So anyway, I think there's some problem here. That's okay. So you know that ChatGPT will be able to answer it, correct? But if you ask me some very specific question, let's say who is the founder of Data Valley and where did he do his schooling? Okay. Let's ask you a very specific question like that. I don't think ChatGPT will know because it will not have information of everybody and the minute details also it will not have. So that information like who is the founder of Data Valley, that information also may not be in Google or anywhere else, correct? So in that case, how will it be able to help us with that information? Okay. So LLMs cannot help us. So that's where RAG comes in. So let's say another example is suppose you have your, your college, wherever you're studying or you have graduated. So you have all your professors, correct? So let's say you want to find out who are the professors working in microscopic multispectral radiograph. Okay. So how will you know, right? So typically if you ask ChatGPT will say, I don't know who your professors are, I don't know what they're doing. But imagine if you gave a PDF which consists of all the professors and their PhD dissertations, okay, or PhD topics, then RAG or retrieval augmented generation will help us in allowing the user to ask any question to get the data, okay, from your college of your professors. Okay. So similarly, you can extend this for many other applications like in a hospital. If you have that, you're building a chatbot, correct? And the chatbot is supposed to answer users' queries for any information related to the hospital, such as who are the hospitals, who are the doctors in a particular specialization, what is their availability, can I book a reservation, so on and so forth. Okay, so so these are the kind of information that it can answer. Okay, now if you look at the core problem, right? So large language models have a knowledge cutoff date. So another problem with LLMs is also that they have a cutoff date. Okay, can someone tell me what is the knowledge cutoff date for ChatGPT? Can someone tell me what is the knowledge cutoff date? So knowledge cutoff date is the date when the model does not have any more data after that, right? So from reactions, okay, yeah. Can someone put it on chat, please? What is the model cutoff date for ChatGPT? So you can go to ChatGPT and ask this question. So I think there's a problem in our network. It's not opening. So
It seems to be a problem on Cloudflare. So that's what happened. That's current
yeah,
issue.
that's okay. I think this is working. Knowledge cutoff date for Claude. Okay, so I'm asking what is the knowledge cutoff date for Claude? Okay, you can see. So knowledge cutoff date is end of January 2025. Okay. Yeah. So what it means is that after this date, it does not have any information, right? So this is another problem. So how does it get the information after January 2025? It basically searches the web, right? So let's say I asked who is the co-founder of or founder of Data Valley. Okay. So if I ask this question, it might not immediately know it. I don't have a relevant information. It could be several with the conversation. Okay. So it's probably ask more details. Okay. Search the web and get. Okay. So let's say I ask this search the web and get this information. So it is searching the web. Can you see it? So if it does not know the answer to this, it searches the web and gets the information. So Mr. Pawan is the founder, correct? Now the point is that is the limitation of large language models, right? They have a cutoff date. Beyond that, they don't know what's happening. So they can also hallucinate, correct? So if you don't have accurate information, they can hallucinate. They lack access to private or proprietary data, right? Suppose you have a college and you have professors in that, you don't have access to any of the information over there, correct? And they also can give you outdated information. So these are all the problems with RAG. Now RAG, what it solves, how does it RAG solve it? Is it retrieves the relevant documents from a knowledge base that you provide. Okay, so this knowledge base is the source of all the information. Okay, now because the knowledge base is the source of the information, it does not provide inaccurate information. Okay, it will give you only from the syllabus. It's more like you're preparing for an exam and it will give only from syllabus, correct? So that's how RAG solves the problem. Okay. Now, again, the same slide I showed you right now. So I'll at a very high level, I'll come back to that slide. So the RAG architecture at a very high level is it operates in three main phases. Okay. The first phase is retriever, second phase is augmentation, and third phase is generator. Okay. So the retrieval phase is basically used to retrieve the documents. Okay. And basically the user query is sent and to retrieving the documents. Augmentation is to enhance it with additional context and additional information, right? And generator is to produce the final answer, correct? So the augmentation involves, so retrieval is go and find relevant documents based on what user is asking. Augmentation is take those documents and take the user's query and then use that for producing the final answer. So generator is basically saying uses the context to generate the final answer. Okay. So this pipeline ensures that LLM has factual relevant information before generating any kind of response. Okay. Now, how does it work in more detail? So let us look at some slides. Okay. So LLM foundations is basically, again, here we are talking about an LLM typically, right, is trained on fixed trained corpus. So this is trained on a lot of data, correct? So what happens is if a prompt is asked saying election results were declared on 2nd Feb, what happened, correct? Now, what is the cutoff date for Claude? Jan 2025. Now, results are asked declared on 2nd Feb, what happened? If we didn't know the answer, LLM will say, sorry, I don't know, right? Why? Because it has not been trained on that. The data which has been trained on is not there until then. So it doesn't have an information. So how will we get it? What we will do is we will take this extra information, what is there, correct, using RAG, correct? We will say, okay, Jan 2025 is a cutoff. So let me add more documents to you from Feb, March, April, May, June, and so on. And I give those documents to you. Now I'll train you, or I'll give that information to you. Now you answer. Okay. So in that case, then it will say, now I know how language works and some details about this world, correct? So it knows the details because we provided that information to it. Okay. So typically how the entire RAG works is based on vector databases. Okay. So vector databases basically are nothing but databases which hold vector embeddings. Okay. So what are vector embeddings? Vector embeddings are basically mathematical representations of the input data that we provide. Okay. So you can provide different type of inputs. Okay. You can provide a JPG, which consists of images. You can provide a doc, which consists of text. You can provide MP3, which is music, and MP4, which is music or video. Okay. Now, any kind of information which you provide as unstructured data, we convert it into embeddings. Okay, or mathematical representations. Okay. So why do we need to convert it into embeddings or mathematical representations? Because each word, right? Let's say I say the classic example that people give is, suppose there is a bank. Okay. So there is a difference between a river bank, okay, and the financial bank. Okay. So let's say someone says the girl is sitting on the river bank. Okay. So in that case, the bank meaning is on the side of the river, correct? Let's say the girl went to the bank to withdraw some money. Okay. So here it means that you are going to a financial institution, right? So the word bank is the same, but the context in which is used in both case sentences is entirely different, correct? So the reason why we converted into vector embeddings is because the context of that word bank is converted into a multi-dimensional space, okay, and saved in a multi-dimensional space, okay, as vector embeddings. Okay. So why is that important? Because tomorrow, suppose I ask a question, right? Was there a cat on the bank? Okay. So if I ask was there a cat on the bank, then if you see the vector embeddings, the sentence called the girl sat on the bank will be returned because it is similar to the bank that you are talking about. The cat, was there a cat sitting on the bank means the river bank, correct? It is more similar to the girl was sitting on the river bank, and that kind of sentence will be retrieved from the vector database because the embeddings of these two statements, right? Which two statements? The first statement is the girl was sitting on the river bank, and the second statement is was there a cat on the bank, right? So was there a cat sitting on the bank? These both are semantically similar in the vector space. Okay. So you and I cannot understand what these numbers mean or how they are, but there is an embedding model which converts these artifacts, which are documents, images, music in an MP4 or videos, into these embeddings and store them in the vector data space. Why are they needed? Because in the future, if a user asks a query, the embeddings of that query are compared with the embeddings in the vector database, and similar documents are fetched from the vector database, and those similar documents are passed to the LLM along with the user query to get the answer. So if you look at it, the next slide, vector database is basically you have a query vector, okay, mountain, okay. So match with all the vectors which are similar to this particular query vector, which is mountain, okay. So in this encoded vectors, it's a huge multi-dimensional space. It's not like two dimensions, multi-dimensional space. It will try to see all the vectors which are similar to mountain, okay. And what matches it? It returns those words whose vector embeddings are closest to the vector embeddings of the user's query. Okay. So any questions still here? Anyone, any questions here? Okay, you can unmute and ask if you have. Otherwise, we'll move on. So next one is, let's take another example. Text corpus learn embeddings. Okay. So we are looking here that in the multi-dimensional space, again, this looks like two-dimensional, but this is not correct. It's actually a multi-dimensional space. Multi-dimensional means two dimensions we know X and Y. 3 dimensions we know X, Y, and Z. Multi-dimensional means more than 3 dimensions. Okay. So here we are seeing that the Berlin, Denver, and Tokyo, right? These are the 3 words, and the vector embeddings corresponding to them are all closely situated with each other. Apple, guava, and orange. The vector embeddings of all of them are closely similar because they're all fruits. Parrot, sparrow, and pigeon, right? The vector embeddings for all of these are similar. Now, who decides whether they're close together or not? Correct? the embedding model decides that they are close to each other because the embedding model has been built by somebody. Okay. So if you want, you can search in the Google, right? Again, you can see in Claude also. So what are the famous embedding models of Google? Okay, so all these big companies build their own embedding models. Okay, so if you see, different companies build their own embedding models, and you will see that some of these embedding models you will be using, correct? So BERT is one embedding model that was developed, right? It uses a bidirectional transformer architecture. Universal sentence encoder, this is also one embedding model. Text to speech and multimodal embeddings. Okay, so like I told you, since the input can be text or images or text or music or video, you have this embedding model, which is text to speech and multimodal embeddings. Multimodal means multiple modes, text, image, there are multiple modes. So Google has developed embedding models that work across different modalities. For instance, model that can embed both text and images into a shared space for cross-modal retrieval tasks. Okay. So, and again, there are several others. We won't get into this, okay, in the interest of time. Now, we have a vector database and the user says prompts, tell me the sales in the last 10 days. Okay. So when this question comes, this particular question is again converted into a vector embedding. Okay. So the embedding it says is the prompt is converted into a prompt vector. Okay. It's no longer text to text comparison, it's embeddings to embeddings comparison. So the prompt vector, which is created by using the same embedding model, is then compared in the vector database of unseen data, which consists of multidimensional vector space. So in this vector space, it will try to see which sentence is closest to the vector of the prompt vector which has been provided. Okay. Now, the idea is you find the nearest neighbors based on the input that has been asked. Okay. Now, based on that input, now if you go back to the original diagram, correct? Here, if you see the additional documents which have been given, right? So I told you that Jan 2025 is the cutoff, correct? Now I asked a question about elections in February, correct? When I asked you about elections in February, we are saying I'm providing additional documents of February, March, April, May, June, and these documents which I provide contain the data of elections happening from Feb, March, April, so on, and Feb, March, April, May, June, July, and so on. Those documents are encoded using the embedding model which I showed here, right? So you can pick any one of these embedding models. So you can pick up the universal sentence encoder or lambda and palm embeddings or any one of these, and then convert them into vector database and store them in the vector database. Okay. Next, when the user asks a query saying, show me election data happened in February, correct? So then what happens? The same embedding model used to encode the query, and then it's, it passes the same embedding model, you can see. Then a similarity search is done against the vector database. Okay. So the similarity search of the vectors are done using cosine similarity. Okay, if you want that one. Now, based on the similar, you will get similar documents, correct? So based on the user's query and the sentences which had similar vector embeddings, right? They both are matched, and you get the similar documents from the vector database. So what vector database will return is not the embeddings, but only the sentences corresponding to the matching embeddings. Okay. So sentences corresponding to the matching embeddings. So these sentences are taken along with the user query. If you see again, query is here. So these documents which are similar and this query which is similar, they both are all in English now. Okay. So the similar documents and the user's query are taken and given as a prompt to the LLM, and the LLM gives a response because the LLM can understand what is the context that is provided and what is the user's query, and then it takes both of them and returns a response back to the user. Okay. So in short, this is the work of high-level flow of RAG, correct? Now, you can see that the role of LLM is pretty much in just accepting some context and returning the response, right? That is pretty much it. But the rest of the role is being played by the vector database and also the embedding model. Clear? So any questions still here before we move on?
No, sir. Clear.
So far is good?
Yeah, yes, it's good, sir.
Okay, okay. So let's move on to the next part in terms of understanding a little bit more deeper into how the inner workings happen. Okay. So document indexing and vector embeddings, vector databases. Okay. So why does indexing matter. Okay. So if you don't apply indexes, correct? So again, like typical databases, you also have indexing over here because you need to make sure that the retrieval is fast, because end of the day, the vector database is also a kind of database, correct? So traditional way is, using keyword search, right? So you can say, I can just use search to search, correct? So suppose I'm saying vehicle, search for all words which have vehicle in them, correct? But the point is, that was how traditionally it was done, correct? Vehicle to vehicle. But certain sentences will not match vehicle exactly. They will probably say car, correct? Now, if you don't explicitly make that mapping, saying that vehicle can be mapped to car, vehicle can be matched to motor, vehicle can match. So if you don't explicitly say and write all these rules, then they will not match. Then it is not efficient, correct? So that's exactly where we have introduced RAG, and that's where the Gen AI has made rapid changes. Okay. So the vector semantic approach says convert documents into high dimensional embeddings.
Your audio was not clear, sir.
Oh, okay.
It's not audible.
Okay. Sorry. I think I was on mute. Sorry. So I'll just repeat again, maybe. Okay. So I think it was on mute. So why does indexing matter? Like I said, in vector database, right? You take these prompts, all these words, and convert it into vector space, correct? So all these are vectors, and what you do is you convert them, you index them, okay, in the vector database, okay, so that the searches are faster, okay. Now, why do we need a vector database? More exactly is, suppose you have vehicle, okay. User says in the sentence something to do with vehicle. Now, the vehicle will not match to car, correct? Because vehicle and car are different. So traditionally, search was like that, correct? It has to exactly match or somewhat similar or part of it. So if I want this to work using a traditional thing, you will have to say vehicle can match to car, vehicle can match to motor, vehicle can match to bus, vehicle can match to moving object, something like that. But in a semantically similar kind of vector space, it automatically takes care of it. Vehicle will automatically match to car, because that's how the embedding model has been trained. Okay. Now, in a vector similar semantic approach, again, since you are converting documents into high dimensional vectors or embeddings, similarity is measured by vector proximity, right? Using cosine similarity, right? So the capturing of the meaning is more important than just keywords. Okay. So some of the keyword vector databases use store and query embeddings efficiently, which such as Pinecone, Deviate, Chroma, and Quadrant. Okay, so they use specialized indexing like HNSW and IBF for fast similarity search over millions of vectors. Okay, so Pinecone is available for free. You can actually take a API key for that. So the next one is embeddings. Okay, so embeddings are mathematical representation of text as vectors. Okay, list of numbers in high dimensional space. Okay, similar meanings have similar vectors. Okay, so how do the embeddings work? A document, for example, the cat sat on the mat becomes 0.2, minus 0.5, 0.8, and so on. Okay, another sentence, a feline relaxed on fabric produces a similar vector. Why? Because these both are similar in meaning. Cat sat on the mat, a feline sat or relaxed on fabric. They both have similar meanings, correct? So the embedding model makes sure that the vectors are almost similar. Okay, that's its job. Now, cosine similarity measures how close they are, correct? So it says, are they opposite 0 or identical 1? Okay, so the closer they are, the better it is, because that is what comes out of the vector database. Okay, so what are the popular embedding models? OpenAI's text embedding. Okay, Google's Gemini's embeddings. Okay, open source sentence transformers, models trained on massive text corpus to capture semantic meaning. Okay. So the embedding dimensions. So typically they have dimensions. Okay. Typically range from 256 to 3072 dimensions. Okay. So more dimensions means more expressiveness, but slower search. Okay. Got it? So you can have more dimension, right? But then you're increasing the latency. Okay. The search speed reduces. So it depends on how much of accuracy you're looking for. Okay. Any questions still here? Yeah. Okay. No questions. Let's move on. Next is the retrieval process. Okay. So the step-by-step retrieval process is query embedding. Okay. So convert user query to embeddings using same model as documents. Okay. So like I showed in this diagram over here, right? So the query is converted encode embedding model using the same encoding model as the one which is used for encoding the documents. Okay. Now, yeah. First is query embedding. Second is similarity search. So find the top K most similar document embeddings using metrics like cosine similarity, like I should mention before, right? Ranking, again, based on what similarity documents you get, you rank it. Okay. So we rank the results by relevance. Okay. Using, again, this is optional, but you can also use cross encoders for that. Next, you have the context window selection, right? Truncate or select the most relevant portions to fit LLM's context window. Okay. So every LLM has a context window where it looks at how much of text it can accept before it can process the data. Correct. So if you're increasing a lot of data to the LLM, it will not be able to process. So it has a limit. Correct. So you have to say out of all the data that is coming from the vector database, what kind of top 10, suppose top 10 results are coming, you can say, I want to send only top 3 results to the LLM along with the user query. Okay. So that is a context window selection. Okay. So what are the challenges? Okay. Some of the challenges are query document mismatch. Okay. So the query and the documents may use different vocabulary. Okay. But still they can be matched as similar documents. Okay. The context window limits. So LLMs can only process so much context, but if you are really sending huge chunks, correct, then can be a problem. Okay. We will talk about chunks soon. Relevance versus coherence. Okay. So retrieved chunks might be relevant, but disconnected. Okay. So end of the day, vector database says I can find them as similar, but it cannot give a guarantee that they are actually relevant. Okay. So similarity is different from relevance, and that's the job of the LLM to make that decision. Okay. So when you give the prompt to the LLM, you need to also make sure that the LLM makes a decision if the data or the context provided from the vector database is sensible or not. If not, it should not give a response. Okay. And LLMs are intelligent enough to make that decision. Next is the retrieval process. Okay. So if you see the retrieval process, again, I'm just explaining that again here. So we have the vector database. Okay. You see that when you say similar documents, it is retrieving from the vector database and augmenting it. Augmenting is adding the query, and generation is passing it to the LLM and along with the prompt to get the response. Okay. So this is the entire RAG process. Now the retrieval process, if you want to say a little bit more detail, right? A little bit more detail, we are saying we have documents. We are converting them into chunks. Okay. So chunks are the main part of the vector database, embeddings creation process. Because suppose you have a document of 100 pages. Can you create the embeddings at one go? No, you cannot. So you created them into small chunks or small pieces. So each of these pieces is passed to the embedding model, and the embeddings are created and stored in the vector database. Okay. So the user asks a question on the top right over here. The user is asking a question. That question is going to the embedding model. These embeddings, those embeddings are converted, compared, and the context is sent to a re-ranker model. Okay. And then from the re-ranker model, again, we take a prompt template that goes to the LLM, and from the LLM, it is the final answer. Okay. So this is just a more detailed pictorial representation of how the whole process pans out. Okay. So I hope by now everyone is clear about how the RAG process works, because I'll dive deeper into strategies and all that right now. Okay. So if you don't understand here, then it'll be difficult to understand those. So anybody, any questions till here? Any questions? Okay. So next is chunking strategies. Okay. So why chunk documents? So documents are too large to embed as single vectors, correct? So chunking breaks them into manageable pieces while preserving context. Okay. So why do we do this? Suppose I have a hospital and a hospital has this user manual and the hospital wants to build a chatbot, correct? Where users can ask any question from that PDF document of the hospital, which has details of doctors, their schedules, what type of treatments they do, which all centers they have, and all that. Now imagine you have a 300-page document, okay? You cannot convert that entire 300 page into one single embedding, correct? So you need to create small chunks. So that is why you create various chunking approaches, okay? So some of the chunking approaches are fixed size chunks, okay? Semantic chunking, hierarchical chunking, or sliding window, okay? So fixed size chunks means basically every n tokens, that is 500 tokens, in gaps of 500 tokens, you simply split that entire document and convert them into embeddings. Semantic chunking means group the sentences or paragraphs by topic. Okay, so if we have a better given topic, you find all those sentences which have similar topics or similar in meaning, and then convert them into embeddings. Hierarchical chunking, correct? So, but the second point, the second one, to make it happen, you need NLP processing for that, correct? The third one is hierarchical chunking. So create nested chunks, okay? So paragraphs and then sentences and then phrases, okay? And more flexible for different query granularities, okay? So again, sliding window means overlapping chunks to preserve context. For example, suppose there are 1000 tokens in the document. 1 to 100 will be one chunk. 90 to let's say 180 is another another chunk, and so on and so forth. So 90 to 100, whatever is there, that is an overlap. Okay. So 90 to 190, for example. So 190 to 200, again, there'll be an overlap, correct? So this overlap will ensure that even if the chunks are stored, the overlap will ensure that whatever is there in the boundary, that boundary text will be passed on to the LLM so that it can answer the question effectively. Okay. So what is the trade-off involved, right? So fixed size means there is no overlap between each chunk. That means exact sharp boundary. Like this PPT is there, no? This page, this slide is one chunk. This slide is another chunk, right? This is fixed size. Sliding window means, if suppose till here of the first, the first chunk will consist of all the text on this page plus till here on the second page. Okay. So the first chunk will consist of overlap between these two pages. So that's how it ensures, the sliding window ensures that there's more context for the LLM. Okay. Now, embedding models and dimensions. So what makes a good embedding model? Okay. So good embedding model becomes good if we have a domain relevance. Okay. So general versus domain specific. Okay. So for example, the domain, having an embedding model which is relevant to the domain that you're working on is much better, because suppose you're working on law domain. So you have an embedding model that works on law domain, is much more better. Okay. Dimensionality. So dimensionality is a trade-off between expressiveness and speed, right? So the more dimensions you have, the better it is. But again, your latency will be slow. So you need to make sure that latency will be high. So you need to make sure that your dimensionality is taken care of. The context length is important because every LLM has a specific context length. Also, the training data on which that embedding model has been trained on. Okay. So it is important to consider all these things, okay, when selecting your embedding model. Okay. Because the quality of the embedding model decides what kind of a RAG quality you're going to get. Okay. So different comparison, if you see, if text embedding 3 small, text embedding 3 large, you see the dimensions 1536 versus 3072, correct? So fast and cost effective for 1536, but most accurate for 3072. Okay. And even if you have complex queries, it can answer 3072. Okay. But we also have 768 dimensions, which are open source and fast and budget conscious. Okay. Or we have multiple languages and which can cater to global applications. Okay. So embedding models improve over time. Re-embedding old documents with newer models can improve retrieval quality. Okay. Next thing is retrieval metrics and evaluation. Okay. So any questions still here? Anyone? Okay, next is retrieval metrics and evaluation. Okay, so how do we know if retrieval works? Okay, so we're getting some retrieval, we are re-ranking it and we're sending the data, but how do we know if it's working properly? Okay, so there are some key metrics like recall, precision. Okay, so recall at the rate K means of all the relevant documents, what percent are in top k results. Okay, so formula which is applied is number of relevant in top k divided by total relevant. Okay, so basically it helps to answer the question, did we find the needle or not? Okay, so in the top, suppose you're getting some k results from the vector database. You know how many are totally relevant versus how many actually came which are relevant. Okay, so that is recall. Okay, precision is saying of the top k results, how many are actually relevant. Okay, so formula is number of relevant in top k divided by total k, which means how many relevant results came out of the total k results that came out. Okay, so basically precision is going to answer the question, how much noise is there. Okay, so you have other metrics like mean reciprocal rank, MRR, which calculates the average position of first relevant result. Okay, so rewards finding relevant documents early. So why is this important? If you find a relevant document which is early in the list, in the top 10 results, if it is early, then suppose I gave only top 2 results and you go to the LLM, that means I can get a good quality result from the RAG, right? If I have a good MRR. Okay. Next is normalized discounted cumulative gain. Okay, accounts for ranking quality. Okay, now this one is basically helping me understand if I'm ranking some results, what kind of quality they have. Okay, so again, we won't get into this, it's way too much for you, but you still keep a note of it. So why this matters for shipping? Poor retrieval means poor generation. Okay, if wrong documents are retrieved, the LLMs can't help. So always evaluate retrieval separately from generation. So that's why make sure that your retrieval process is strong, because the generation process is solely dependent on how the quality of data comes out in the retrieval stage. Okay. So next is query expansion and rewriting. Okay. So user asks, what are the side effects? Okay. So, but your documents use adverse reactions. So, okay. So the query doesn't match, right? So what is the solution? Transformation. Okay. So you expand the query, okay, generate multiple reformulations of the query. Okay. So what are the side effects? Adverse reactions, negative outcomes, complications, risks, and retrieve all the versions and then combine the results. Okay. So this basically increases the recall. Okay. It helps you increase the recall, but we increase noise as well. Okay. So the other approach is query rewriting. Okay. So you're basically saying side effects can be written as pharmaceutical adverse reactions, which is more specific. Okay. And instead of saying just the how's the stock, what is the current stock price of the company for clarification. Okay. So you can also do hypothetical document embeddings. Okay. Where you generate hypothetical documents that might answer the query. Embed these hypothetical documents instead of the query itself. Okay. So often better than embedding the direct query here. But again, there is an implementation trade-off. Okay. So better retrieval versus higher latency. Okay, extra LLMs cost, extra LLMs calls, and the extra cost. Okay, so again, some of these are all trade-offs which you'll have to consider when you're deciding which strategy you need to go for. Okay, next one is re-ranking and context selection. Okay, now why do we need to re-rank it? Okay, now typically we have seen that a retriever is used to find the documents quickly, but may not rank them perfectly. Okay, so a re-ranker uses a more sophisticated model to refine the order. Okay, so what a vector database gives us is the chunks, correct, which we send to the vector database. But a re-ranker uses a more sophisticated model to refine the order. Okay, so what is the re-ranking process? The retriever returns top 100 candidates. Okay, re-ranker scores each candidate against the query. Okay, and returns top 10 re-ranked results to the LLM. So it makes sure that whatever is going to the LLM are best results based on the query that is coming in. Okay. So what are the re-ranking models? Cross encoders. Okay. So cross encoders directly score query document pairs more accurate. Examples include the Cohere re-rank, the BGE re-ranker large, and open source options are also available. So context selections, after re-ranking, decide what to pass to the LLM. So even after re-ranking, you still need to make a decision. Okay. Should I send the full documents or just the top passages? Concatenate directly or summarize retrieved content, and also consider the LLM's context window and token limits. Okay. So re-ranking adds more latency because you're doing some extra process, correct? But it simply significantly improves the quality, correct? So for production systems, measure if the improvement justifies the cost, because you're incurring extra cost. So you have to make sure that it is helping you in that aspect. Otherwise, you're unnecessarily increasing the latency or increasing the time it takes to process the request for the user. The multi-stage retrieval is basically you have again, the retrieval, again, we have put it down into multiple stages. So stage 1 is basically coarse retrieval. I think we already saw this. So let's move on. So chunking strategies, okay, there are various chunking strategies, okay, which I use like fixed size chunking, semantic chunking. I think we already saw this, okay, the various chunking strategies, fixed size chunking, recursive chunking, and all that we have seen in one of our earlier slides, okay. So let's move on in the interest of time. So next is handling long documents, okay. Now let's say we have a document which is a PDF of the hospital, and that is a 300-page document, okay. Now, if it is a 300-page document, it is not easy for someone to, do the, chunking of the entire document, right? So what we do is we have different strategies for creating the chunks, like I mentioned above, okay? Now, here we are looking at a few strategies again, like the hierarchical retrieval, okay? So we create document level, section level, chunk level, and then convert into chunks and create embeddings for them. So we again have stored the metadata with chunks so that it's easy to filter them later on. Okay. So for example, if user says find legal documents from 2023 about contracts, okay, so it becomes easy to handle because the metadata is already filtered. Now, we have again summary-based retrieval and tree-based structures. We won't get into this in detail. So one thing I wanted to talk about over here is the augmentation side of view. Okay. So combining the user query with retrieve context before sending it to the LLM. So that is what is augmentation we discussed before. Okay. So what are the key challenges? So GPT, some of them have context window limits. Okay. GPT-4 has 128,000 tokens as a context window. Okay. So older models have just 4,000 tokens. Okay. So each retrieved documents is considered as tokens, correct? So we need to be cautious. So need to fit system prompt. So what all goes into that token, which goes to the LLM? System prompt, retrieve documents, query plus generation space. Okay. So all of these get into that. So how do you make sure that your context window, augmentation and context window is handled properly? Okay. So one is prioritization. Okay. So whatever documents you get, first rank them by relevance. Include only top documents till window is full and drop the low rank documents. Okay, that is prioritization. Next is compression. Compression involves summarize each document before inclusion. Don't send the entire context which has come from the LLM, from the vector database. Summarize it. Okay. Use extractive summarization and loses details but saves space. Third one is query guided selection. So for each retrieved document, extract relevant sections. Okay. So what we are doing is from the extracted document, again, we'll take relevant sections only. Only include excerpts, not full documents again. Don't send the entire document, even if it's coming from vector database, take only a small part. And then LLM can infer the full context because LLMs can even process the information or give good answers based on limited context, right? But of course, there is always a compromise on your quality if you're not able to get the proper context. As you know, if you're not able to get the relevant sections properly, okay? So the generation phase is primarily again is important because it is the final stage in the RAG process. Okay, this is the final stage after which the response goes to the user. So in this stage, you have to take care of prompt engineering. Okay, so this is important because prompt engineering is what is used to send to the LLM to respond. Okay, next is temperature and sampling. So if you have low temperature, it is more deterministic. Okay, it sticks to the facts in the context. If you give it a high temperature to the LLM, then it will be more creative and may hallucinate. So typically for RAG, you prefer lower temperature. Now, what is the end-to-end RAG pipeline? I think we already saw this. You get the user query. Okay, you do pre-processing it. Okay, do query embeddings, then do the retrieval. Okay, and then do the re-ranking. Okay, and then augmentation, then generation, then post-processing. Like, again, add citations, format output, or remove any PII. PII is personally identifiable information, right? Like your phone number, emails, or whatever, correct? So even if the LLM is sending the data for some reason, you should be able to do processing before you send the response back to the user. Okay. So that is a high level RAG pipeline. Now, what are the common pitfalls and solutions? Okay. So the common pitfalls that we see are garbage in, garbage out. Okay. So if you do bad embeddings or if you have a bad retrieval logic, then your generation will be pathetic. So evaluate retrieval quality separately, use NDCG or MRR metrics like we discussed before. Context overload. If you have too much of context, it confuses the LLM. Okay. So aggressively filtering, re-ranking and summarization will help. outdated embeddings. So suppose you have very old embeddings, right? So old embedding model, if you use long back, it may not be as efficient. So if you got a new embedding model, you should use that. Okay. So keep re-embedding periodically with new models so that you can get more accuracy because the models are becoming better and better by the day. Query document mismatch. Okay. So the query uses a different language than the documents. Okay. So if you're, the solution for this is expand your query, rewrite or domain or create domain specific embeddings to solve this. Okay. Next is practical considerations for shipping a RAG solution. Okay. So always keep performance, cost and scalability in mind. Okay. Performance, minimize the retrieval latency less than 200 milliseconds. Use appropriate nearest neighbor search, HNSW and IVF, and cache the embeddings and results when possible so that you don't hit the vector database again and again. Okay. So cost is very important to keep in mind because every query to the LLM will cost you money. Okay. And at scale, it will very quickly become huge, right? So consider the various model choices. Smaller models versus smaller models will give you less cost, but again, a little bit less accurate. So you have to take a decision there. Scalability, how many documents do you want to consider? How many queries per second are you going to hit? And how many users are you going to consider for this solution? So these are all the things which you should consider for shipping your RAG applications. Okay, performance, cost, and scalability. So what are the advanced RAG techniques? The advanced RAG techniques are hybrid search, okay, where you combine the keyword search plus semantic search, right? Graph-based retrieval represent documents as a knowledge graph, okay? Iterative retrieval is where you retrieve documents, generate partial response, retrieve more based on generation, and you do the retrieval approach. Multimodal RAG is basically you can handle text, images, tables, or code, multiple modes of giving the input, okay? That is multimodal RAG. What are the evaluations and metrics? So again, there are three levels of evaluation. The evaluation at the retrieval stage, evaluation at the generation stage, and end-to-end evaluation. Okay. So evaluation at the retrieval stage is basically we are saying, are we finding the right documents? Okay. What are the metrics? Recall at the rate K, precision at the rate K, NTCG and MRR. Okay. So that is the retrieval stage evaluation metrics. Generation evaluation is LLM generating good responses. Metrics are blue, rouge, right? And of course, human evaluation also. Okay. End-to-end evaluation is, does the full RAG system solve the user problem? Okay. So methods are user satisfaction surveys, task success rate, A/B testing. Okay. So practical evaluation is basically create a test set of queries with human judged correct answers, run the RAG pipeline on test set, measure retrieval accuracy, generation quality, end-to-end success, and use for version comparison. Okay. Now RAG is a journey, okay, not a destination. Okay. So it is not a single one-time thing. You just put it and immediately it happens. It requires a lot of iterations. Okay. So it's not magic. RAG solves real problems. Okay. It's not magic. It depends on the quality of the retrieval augmentation. And so RAG solves real problems is if it has outdated knowledge or it can provide hallucination and incorrect information. But it helps you when you have private data. So it's not magic. Again, the quality depends on retrieval, augmentation, and generation phases, and you should take care of them. So evaluate early and often keep evaluating it to make sure that you're giving you right results at each stage. Start from a simple pipeline and then evolve and monitor continuously in production. Okay. So the RAG stack typically consists of vector databases such as Pinecone and Deviate. Okay. Embedding models can be OpenAI. LLMs can be GPT-4 Claude. Orchestration framework can be LangChain and Llama Index. And monitoring can be custom or off-the-shelf kind of monitoring solutions. Okay. So finally, RAG is a journey, not a destination. So RAG is powerful, but requires thoughtful implementation. Success comes from understanding each component, measuring what matters, and iterating based on real-world performance. Okay. So that's it from my side. Do you have any questions? Anyone? Yeah. Anybody has any questions? Yeah. Data Valley team, do you have anything for me, or else we can call it a day? Yeah, I can share the PPT. One second, I'll put the PPT right here. Wait. Okay. Okay, I'm putting it here. Okay. Yeah. So data validity team, I hope it's okay to share the PPT, or do you want to share it?
think it
It's okay, you
seems
can
you have shared it already. Right?
Is it okay or I can remove it?
That's fine. No problem.
Okay, okay, fine. Okay, that's it, people. Thanks for your time, and I hope it is useful. Okay, we'll call it a day. Okay, thank you. Bye.